Here we are, sound. Sound is what we're going to talk about. It's a little more complicated than you might think. Sound is this pressure wave, a longitudinal wave. If you take a look at the pictures, either one of these animations, and follow one spot, you'll find it doesn't travel from one side to the other. It just goes back and forth, back and forth. Basically, sound is nothing more than a pressure wave, a compression. In other words, the energy forces a compression within the medium it's transmitting through. Remember, waves are nothing more than a movement of energy, not matter. So these little tiny dots, they're not traveling across the screen. Notice as well, from compressed point to compressed point would be one wavelength. It's analogous. These compressed areas are analogous to a crest, and what's called a rarefied spot is analogous to a trough, something you might wish to know. So there you have it, just what we said. Compression, things are squeezed together. Rarefaction, they're rarefied, they're pulled apart, low pressure. It turns out you cannot make a sound if you don't have a medium. All longitudinal waves need a medium. There's an old poster, Alien in space. No one can hear you scream. That's so true because there's no air in space. In fact, how boring Star Wars and other movies would sound if they really did it true to science. You'd see an explosion, but you wouldn't hear a thing. When you make a sound, you're increasing the amplitude of that wave. We tend to measure this in decibels when it comes to sound. It's something called a logarithmic scale, meaning every 10 decibels higher is 10 times more intense, an intense sound. This grows rather quickly in terms of what you hear. For example, something quiet, what's considered quiet, would be 50 decibels. 60 is conversation. Then we jump to 70 and it's busy traffic. This is 10 times more intense than the last one, and 10 times more intense than the next one. Realize hearing damage occurs somewhere around here, between 80 and 90. When we hear noises, there's a range at which we do hear them. 20 to 20,000 hertz. That's not an absolute number. Approximately. Some people hear a little lower. Some people hear a little higher. When they hear anything lower than 20 hertz would be infrasonic. And anything above 20,000 hertz would be ultrasonic. An example of an infrasonic thing would be elephants. Elephants transmit sound somewhere around 3 hertz. We can't hear them, but they can. Ultrasonic, you've probably heard of bats and things like that. Ultrasonic, sounds that you can't hear because they're just way too high. The speed of sound can change, and that can depend on a few things. The actual medium it's traveling through, in other words, substance, and the temperature. It turns out when air, for example, is warmer, sound travels faster. And that should make sense because we're talking about molecules moving. And as you heat something up, molecules move faster. And so it's already moving fairly fast, and sound is a transmission of the wave by means of a molecule moving. We have this nice equation so you can determine the speed of sound. It's 330 plus 0.6 times your temperature. Your temperature needs to be in Celsius. As I mentioned before, the substance itself makes a difference. In water, speed of sound is about 4 times faster, steel 15 times faster than air. Of course, in a vacuum, we're not talking a Hoover, the vacuum of space. There is no sound because there's no medium. Resonance is a really great application of sound. It turns out when you make a sound, you force a vibration of your vocal cords. Other objects will vibrate as well based on the sound that is hitting them. You've probably heard the old break a wine glass, singing at just the right note. This actually can happen. We have some definitions to talk about. A forced vibration, and that's exactly as it sounds. I'm going to make something vibrate. I'm going to force it to vibrate. However, all objects have a frequency which they naturally vibrate. If you take a wine glass and you tap it, it will kind of ring, or a bell. You'll hit it and it'll just, for a long time after, it'll just ding. So this is its natural frequency. What happens if you were to force a vibration at that natural frequency? Well, you get a very big amplitude. Look at the monkey on the right here, and you can see what happens. The amplitude of this thing grows bigger and bigger. On the left, when they don't match, right, he's pushing at a different timing than this thing is swinging. And it comes to a very quick stop. A good example, and you might want to look this up, go ahead and Google this, the Tacoma Narrows Bridge. Watch the video. You get to watch a bridge collapse because the natural frequency at which this bridge was vibrating matched a forced vibration of the wind, and it actually collapsed. Speaking of sound, when you have two sounds interfering with one another, we've often talked about interference before, but when they interfere, if you look here, sound 1 and sound 2 up here, sometimes they're in sync or in phase, and other times they're out of phase. And so you'd hear, if this were sound, you'd hear a loud sound, and you'd hear a soft sound. A loud sound, soft sound. So you have that constructive and destructive interference. And if you hear one of those, loud and soft, one of them in 1 second, they are 1 hertz apart. If you hear two of them, they are 2 hertz apart. So maybe it's a 440 hertz sound and a 442 hertz sound. And this is how the old piano tuners would tune their pianos, listening to the interference between their tuning fork and the sound that the piano was making. They'd listen for those beats. No beats, it would be in tune.